Good morning. Welcome to this plenary lecture by Professor Franco Brezzi. Professor Brezzi graduated in 1967 from the University of Pavia with a thesis in mathematical analysis with Professor Enrico Magenes. In 1976, he became a professor in mathematical analysis. And since then, apart from a year spent at the Politecnico of Torino in Italy, he has been a professor at the University of Pavia. And he has been director of the prestigious IMATI Institute of Numerical Analysis there. And now, since a few years, he is professor of IUS, which is the Institute of Advanced Studies in Pavia. Franco Brezzi is certainly one of the leading numerical analyst in the whole world. He is behind very many discoveries in the analysis of finite element methods for partial differential equations. He is the author of the celebrated Brezzi condition, which is a necessary sufficient condition for stability and convergence of mixed variational problems. He is also the author of a very famous theory on for the treatment of bifurcating solutions for nonlinear partial differential equations. He has contributed very substantially to the theory of convection-dominated problems, from numerical approximation of convection-dominated problems for this continuous hierarchy method, and more recently on mimetic finite differences and the virtual element method. Franco has been awarded with very many prestigious awards. Let me just mention 4 of them. One is he was the first mathematician, the only one, as far as I know, mathematician who got the Gauss-Newton medal from the International Association of Computational Mechanics. He won the von Neumann Award from Siam, the Blaise Pascal medal from the European Academy of Sciences, and very recently, a month ago, actually, the Leonard Euler medal from ICOMAS. Today, Franco Brezzi will talk on the great beauty of virtual element methods.
Okay, thank you, Alfio, for your very nice presentation. Actually, we did agree that we will make a short one, but okay, you can count on friends for a longer one. Can you hear me? Yeah. Okay. If I'm too loud, you make a sign. Okay, so I also want to thank the organizers and at all the levels, the panels that chose me. It's a great honor for me to be here, and I'm very grateful. So I will try to do my best. Let's see. Okay, here, well, actually, it's not really, these talks come essentially out of several papers. Is wrong. Please don't start complaining because the first slide is wrong. It's not totally wrong. It means that these are. It will be those papers are the content of the very last part of the talk. I realize, I know, I share the opinion that a plenary lecture in a meeting like this one should not deal with the very last result of the speaker, but rather with the panorama and the overlook on the general subject of his field. And actually I will do, because you see essentially the virtual elements will be 5, 6, 7. Okay. Before that, it will be, generic stuff on scientific computing, what are our targets, how do we work, and so on. What are the type of results that we are after. But, okay, I apologize. you possibly know that there is a part of mathematicians that have definitely a childish part in their personality. This is surely my case, and in particular, for me, the last toy is the most wonderful one. So I couldn't resist to speak about my last toy, which is virtual element methods. Okay, so let's see. Well, first, I will just recall physical equations. I will not deal with them directly, it's just, and I will not, I'm not here to teach you what are the Maxwell equations. It's just to recall that the typical enemy that we fight are equations of this type, like, Maxwell as this one. We will see Navier-Stokes equation in the next slide. Though I took two equations that you can even find on t-shirts. So, okay, it's maybe you don't know the how and the why. Many among you could teach me everything about those equations. I mean, but some other will not be interested, never been interested in those. Okay, but what I would like to point out, so actually I will use the pointer here, to give to the line, to under what line, because on the white you cannot see. So there will be physical quantities like the electric displacements or the magnetic induction, of which you take the divergence and or the time derivative. Okay, and there will be other quantities like the electric field E and the magnetic field H, of which you take the curl. And actually, if you remember something on your basic physics course, if you have two media, you know that the normal component of the electric displacement is continuous, and the same is for magnetic induction, while is the tangential components of the electric field and of the magnetic field, which are continuous. So they are sort of a different nature. And of course, this could also be interpreted by saying that the D and B are two forms, while E and H are one forms. Okay, so now this is, but here instead you have quantities like, U are the velocities, which you assume need to, in general, need to be continuous. You expect them to be continuous. And okay, the pressure, and also the pressure instead is something that even though you take the gradient in the strong form of the equation, but you could think of as as a tree form. Okay, now actually what counts and what is the way of writing equations on a part of the numerical analysis, in particular for finite elements and then for virtual elements, is the variational formulation. Well, this variational formulation, I took here the simplest possible example of a variational formulation. You want to solve a Poisson problem, and so you look for a function v, which is, say, L2 gradient in L2 and 0 on the boundary, and you want the minus Laplace of u being equal to f, and many of you know extremely well, much better than me, that the solution u could be characterized as the solution of this last equation, which could be thought as the Euler-Lagrange equation of a minimum problem. Okay. Well, and actually the regularity that we need is the regularity that allow us to write the variational formulation. Now, what about what has this to do with numerical methods and finite elements? Basically, this Galerkin formulation first. The Galerkin formulation starts from the variational formulation and essentially say, okay, instead of looking for the equation in a space and having the test function in the same space infinite dimensional, you take a finite dimensional subspace and you look for a solution in the finite dimensional subspace and you write down the equations, which is basically this line here, okay? You write down the equation that has to be true for every, I cannot get it on the other side. Okay, yes. You get it for all the test function in the subspace. Well, in this particular case, it's really an easy exercise to show that the solution of this problem is unique and also satisfy this estimate on this last formula here, that is an estimate which has is an interesting meaning. Actually, in this particular case, the constant c is 1, but in general you have a constant. And the estimate tells you that your method will be as good as the choice of the subspace is good for approximating the solution. So, okay, you have a problem. You have a solution that you don't know, but you have an idea of what are the properties, how does it look like, and so on. And then you choose the subspaces, and within the subspace, you want to theoretically approximate the solution. You look what would be the best approximation of the solution within the subspace. And this is basically the best you can do. You cannot beat that. Right? There is no miracle. If you stay inside the subspace, that's it. So we call a result like this optimal, because given the subspace, you cannot have anything better. Okay. Okay. And more generally, the analysis of our procedures assumes, the mathematics assumes that you have a sequence of the compositions. And then you want to prove that the sequence of solutions converges to the solution of the problem, and possibly also to connect the speed of convergence with the property of the sequence. Okay. Now, let us take a particular way of choosing those sequences, which is the finite element. This is extremely popular, is, you know, the core of most, say, 80% of the commercial code for industrial computing. So it is, you know, a very fundamental method. And okay, so the idea with finite element methods is, you know, finite here is not in contrast of infinite, but is in contrast with infinitesimal. Okay, so it means that it's big. The finite element is that, you know, the small cube of physics that goes to 0, it does not go to 0, but you stop it at a certain size, a finite size, not infinitesimal. Okay, so typically you take your domain, I draw a square, of course in general it will not be a square, and you decompose it in, for instance, in triangles. Okay, this is the simplest and most popular way of decomposing it. And then you take, lowest level is you take V sub h, so the subspace of H1, as the space of functions that are polynomials degree less than or equal than 1 in each triangle. And typically their value will be identified by their values at the nodes, the vertices of the triangles. Okay. Okay. Well, of course, why should you take just a polynomial degree less than or equal than 1? You could take polynomial less than or equal than 2, degree less than or equal than 2. And so you have different types of degree approximation, which are on a given decomposition you have different degrees of the polynomials, or if you fix the degree you have a sequence of the composition. And typically the analysis of mathematicians consists in finding a way of measuring the speed of convergence, like, you know, h in this case will be the biggest diameter of the triangles. And you will say, okay, the distance in between my approximate solution and the true one goes like this last formula there, provided that you have some constant that limits the sequence of the compositions. You have some sort of uniform non-degeneracy of the sequence of the composition. So that you will have a constant that depends on that. Okay, so this is fine. And so for instance, these are now what we call the degrees of freedom. Degrees of freedom is the values that you use for identifying a function. Remember that in the computer you don't put the function, you put some identifier to be in the finite dimensional space. So those are, it's nice, elegant. And then, okay, so why aren't you satisfied with that? Well, there is actually what you expect from your solution is not only the speed of convergence. We already saw, for instance, in the lecture of Emmanuel Candes, that an example of applications in which, not of finite elements, problems in which what is really important is that, say, the physician looks at the picture, NMR or CAT scanning, and say, here there is something wrong, or relax, there is nothing wrong. And you know, this capability of interpreting the picture is not one-to-one related to the error, say L2 error, in between your image and the true one. And the same is also true when an engineer will look at what's going on for a particular choice, say, of the shape of an air, of a wing, or, you know, the body of the car. This is... So he has to draw guesses out of it of what should be modified in order to have an improved solution. And for that, you need, for instance, methods that respect, or rather, that produce a solution that respects some physical property. For instance, if you have a concentration and you get some even minor negative result, this is upsetting, okay? To have a concentration that becomes negative around some place in the domain, even if it's not too negative, because it is close to the true solution, which is positive. Also, particularly important are conservation properties. So you want that your numerical method will, say, conserve the total mass, the total charge, or, you know, or so the energy, whatever. Depending on the problem, you have a certain amount of physical quantities that you would like to preserve. And for that, it is important to deal with subspaces which have, in a sense, the minimum continuity properties. So if you want them, the solution in the subspace to be very smooth, often you have to give up some conservation law. Instead, if you want to have a method that respects the conservation laws, it is often convenient, almost compulsory, to use the minimum regularity that is needed in order to have the variational formulation. So, for instance, you have different spaces that will be used, which are, you know, okay, L2, no regularity, HDiv, you have a normal component. Well, we shall see actually in the next slide. Okay, so what has to be continuous in order to be in the space? So in order to be in L2, you don't need nothing. In order to be in HDiv, you need the continuity of the normal component, H curl continuity tangential component, and in H grad, which is the usual H1, is the continuity of all the components. I mean, if a function is Okay, I'm not saying that the function of H1 are continuous, but if you have a function which is smooth in each piece, then it will be in H1 if and only if it is continuous in the interface, okay? Okay, and so you have a basic, as we had the piecewise linear for what we call nodal values, you have the basic ingredients for the discretization of all those spaces. So for instance, for P1, you have, say, on a tetrahedron now, I went to 3D, you have, you know, four degrees of freedom on each tetrahedron. And then instead, if you want to be in H curl, so you have the tangential component to be continuous. Oh, okay, the first one I think is attributed this to current. That's okay, it's very standard. This is much more recent. They would come by Whitney, but this goes under the name of Nedelec. N is for Nedelec, and the lowest order Nedelec space. And these are for having the normal component continuous. You use as degrees of freedom the normal component, which is constant on each face, and this is the lowest order Raviartomar space. And then, okay, of course, for discretizing L2, you don't need anything, so you can take piecewise constants. The simplest choice for L2 is piecewise constant. Okay, and all this is extremely elegant. Okay, but already when you go out of triangles, you use quadrilaterals, your liberty is diminished. You are not so free, you're not so elegant anymore. For instance, for quadrilaterals, a shape like that is allowed, yes, but the other ones you have, you know, 2 points that coalesce, or 3 points that get aligned, or the domain that becomes concave, or not lose convexity. Those ones are not allowed. So you have limitations, and also, this is not the only trouble, you also have an objective loss of beauty, like, you know, okay, this when I say the most elegant choice, these are spaces by Doug Arnold and Avanu. Avanu, I think, is here. Is really the most elegant possibility of having, you know, this phase conforming or H-div conforming, oh no, this is H curl, conforming on a cube, not even distorted. So you say that you see by those tiny examples that when you go out of triangles, you start little by little to get into troubles. And what is even worse is what happens when you want to have C1 elements. Now, C1 elements, there are, of course, in the literature, like, you know, this Zier-Klaftocher, reduced Zier-Klaftocher, Algiris, Bell, and so on. But for instance, if you look at the one top right, reduced ACT, those functions are the functions inside are functions which are polynomials of degree 3 in each subtriangle. So you have 30, dimension 30, and then you require that inside is C1, and you have functions which are polynomial of degree 3 on the edges, but the normal component is degree 1. Okay, you can do it, it works very nicely. But when you have to program it, this is something that you never forget. If you ask somebody, did you ever have to program C1 elements? Well, I'm not sure, maybe yes, maybe no. Surely no. He didn't, he or she didn't. If you do it, you remember. It's like, it's an older stuff, but if you had any experience of the cod liver oil, okay? If you tasted cod liver oil once, you remember. Did you ever taste it? Yes. It's so disgusting that you cannot forget. Oh, okay, this is also in some other language, okay? So it's something that is unforgettable. So, I mean, it can be done, it works, but it's not really what you would like to do in life. Okay, instead, my beloved virtual element methods allow you a decomposition like this one, okay? The composition like this one is perfectly legitimate. And notice that, okay, you have elements which are not convex. These are 4 elements, okay? The composition of the big rectangle in 4 elements, the blue element which has 8 nodes, the yellow element 12 nodes, the pink element has 14 nodes, and the green element is 1 element with 41 nodes. And you can also have, you see these 3 nodes all together, if some node correlates, it still works. So it's incredibly robust with respect to the shape of the element, and so we are very proud of it, needless to say. And okay, can we do this in 3 dimensions? Yes, you can do 3 dimensions. You can do elements like that in 3 dimensions. And you can even take a bigger box that is, you know, a 3-dimensional domain minus those ones, and still it works. So, wow. Well, okay, let's face it, this is not by far the first type of element. We are not the guys that invented polygonal or polyhedral elements. There is a wide literature. As far as I know, it started, the earliest paper, which is actually already a book, is by Watchpress in '75. So this is basically 40 years ago, and you see that there are important contributions all over up to 2013. So it keeps going. Okay? So there is a wide literature on non-triangular, non-tetrahedral, or more general shapes. And the idea is, okay, why would you take a more general shape? Well, there are reasons for doing that. In many problems, you can take just triangles, it's okay, or tetrahedra. In other problems, it is convenient, in particular when you have an internal interface that can move, for instance, like, you know, in 2-phase flows. Okay? Then the difference between one phase and the other phase is a line that moves. And then it is much better to sort of keep some structured grid behind, but then move the interface, and this in 2 and 3 dimensions will create strange shapes. Or you might have an internal structure, microstructure that you want to follow, or you have a crack that propagates and you want to follow the crack, and so on. I mean, you have, and also you don't want actually your grid to orient the solution. So if you have more rounded elements, this helps a lot. So, okay, this is just to say that we are not inventing too much, but ours have some. And so these are possible decompositions that we can do. And, or, for instance, this is something that comes out useful, and many other non-polygonal elements do not have. So assume that in a part of your domain, you need a particular accuracy, because you have a boundary layer, because you have an internal layer, because you want it. Okay? And so you want, you know, a fine grid. But then you don't want the fine grid to be all over the domain because it's too expensive. So you have to, in general, you start from a fine region going bigger and bigger and bigger until you get to the coarse grid. In here, for instance, if you take those those elements there in the middle, which are, you know, they are big, but they are on the boundary with the small ones, from the Venn point of view, those are polygons with 11 edges. And even though the edges are aligned, you don't care. Okay? So this really helps a lot. And, but of course, you can do even worse. For instance, okay, we have in our team, we have a guy which is Alessandro Russo, which, well, no, he's not crazy, he's perfectly normal, but you know, it's imaginative. So he said, okay, why don't you take a decomposition like this one? So he took a decomposition into squares, but then inside each square, he took out a random polygon with 9 edges. So for instance, this is one example. You know, in the right, you see the first one up there is blown up there. And if you look at it, you see that in each square you have 2 elements. You have one element which is the pink one, and another element which is the blue one. And okay, the pink one has 9 edges, the blue one has 13 edges, and is not even simply connected. So will you be able to solve with a grid like that? So okay, we took some particular case, constructed, of course. It does not come from a true problem, but in such a way that you could look at the whole surface without going through. So you don't need the surface to be transparent. This is the glasnost region, okay? So this will be the exact solution, okay? This you have the analytic expression, and if you solve with this crazy mesh, okay, it works. And if you want, you know, to go finer, take a finer grid, then this is. And okay, you possibly could see that the error is 0.07, and this, when you double the number of elements, is 0.019, and then if you double again, is 0.005. Essentially, when you double, you reduce the error by a factor 4. So it means it goes like h squared, which is, you know, what you expect if you are exact on linear. And then, okay, so he sent us this amaze your friends with those results. And some other guy in the team said, oh, blah, 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 okay, why don't you do this? If you really want to amaze your friends, do that or that. Okay, you possibly like the painting because they are very nice or recognize them. Is Escher, and okay, he did. So I said, okay. He took a little horse, a little Pegasus, and he made a polygon that looks like a Pegasus, and then, but in such a way that you could put them together. No, okay. Then he numbered the nodes, come out to have 82 nodes. So this is a polygon with 82 nodes. And 82 edges. There is also the one with the edges. Why is it? Okay. And then you see you can put them together. So you have a 2 by 2 grid. And of course, as you do the 2 by 2, you could do the 20 by 20. Now, okay, let's be serious. I don't think that you will ever have to solve a problem with that grid. Okay. But, okay, just to see whether it works or not, okay, why not to try? You know, note that on the boundary, you know, it's a total disaster, okay? So, let's try. It works. Yeah? It still works. I mean, you have, and you are exact on linears, okay? And then you take a 40 by 40 Pegasus, and this works better. So you see the errors goes down like h to the square. So, okay, this is really, I hope that at this point I have convinced you that you are interested in virtual elements that they have some merits. So I convinced you, I hope that I convinced you that my toy has some, is a nice toy. Okay? And so what are the characteristics of these methods? One feature which is common to other polyhedral elements is that the functions inside each element, well, they contain all polynomials, but they contain many other polynomials. For instance, in the Pegasus, you have P1, 3, and then you have 79 more, which are not polynomials. But contrary to other methods on polyhedral elements, we don't even try, usually our solutions are, our functions are solutions of PDE equation or system of PDE equations that we do not attempt to approximate. So we want to work only with what we know, without doing a subgrid resolution. So this is somehow the name of the game. And okay, a nice feature that they have is that they reproduce, if you are using polynomial of degree k, they will give you the exact solution whenever this is a polynomial of degree k. And not only, but contrary to other methods for polygonals and polyhedra, we have a whole family now. So it's not only nodal, but also face, edge, and so on. We have the whole structure. Okay. And what is the general philosophy? The general philosophy for working with them, to define those functions, is to start from the boundary. Okay, so in 2D, you start, for instance, from the edges. Well, in 1D, you can take a polynomial. That's not so expensive. With one edge, you take polynomials to a certain degree. And then inside, you say, okay, I want functions which are, are harmonic. Okay, but this is the less interesting case because it was done. You take Laplacian, which is a polynomial of degree 2, 3, 4, whatever. And then you are careful that all polynomials of a certain degree are inside. Okay, you want to be exact on all the polynomials up to a certain degree. And then let us see an example, okay? This you take functions on 2D that on each edge are polynomial of degree k, and inside have Laplacian, which is a polynomial of degree k minus 2. So now this space here is finite dimensional, and it contains all the polynomials degree k. But of course, in general, it contains more. Okay. And then, as degrees of freedom, you take the values of the vertices, the moments on each edge, and the moments inside. Not the moments of the Laplacian, the moments of the function. Okay, now, I will go very quickly through the whole family. Well, these are, all the papers are on my web page. And also I think that the slides will be made available, so I mean, you can find the precise definition. So, but essentially the philosophy is this one, okay? Look at I put the magenta on this pk minus 2 because in principle, if you want, you could take instead Laplacian of degree k instead of k minus 2. It will still contain all polynomials degree k with something more. Okay? So you have a certain freedom. And then also you have a trick that I will not describe in details that we call the three-card Monte trick, being Italian. Okay, this is one of the Italian specialties. And it looks like magic, but which allows you to take, for instance, projections on polynomials, L2 projection on polynomials a certain degree. Okay, this is a crucial instrument. And, okay, a rough way of describing is, okay, you take this procedure, which is a simple one, strictly speaking, is wrong. But since there is a parallel universe in which this procedure is correct, then the fact that it works there make it work even here. So do it and it will work. And it does, okay? You can prove that it works. It's a tricky stuff, but okay, I see that you are not so confident, but believe me, okay, it works. I mean, we did a lot of experiments. It always works. Okay. So this is for the Tricarmonte, and those are possible choices of, say, the nodal ones in 2D. And then I will, very quickly, for more general geometry, you have, this k equal 1, functions which are linear on each edge and harmonic inside, or quadratic on each edge and Laplacian constant. And on 3D, again, okay, you see that those magenta numbers could be changed. In 3D, you have to work with something which is a Vem on the face, and then you also prescribe the Laplacian inside. And then basically, okay, and the degrees of freedom are always, essentially, moments, okay? Moments on the edge, moments on the face, moments inside. Okay. And then when you have to do the HDiv elements, you prescribe a boundary value for the normal component, and inside you solve a div rot. This is a two-dimensional curl, the rot. And there you have the magenta and the pink, those degrees you can change. And you have, in this particular case, you have very interesting variants. Like, for instance, just the most famous Ravière-Thomas case, they come out as a variant of this. And again, the degrees of freedom are moments. I will go very quickly because, okay, if you want really to study them, it takes 3 minutes per slides, and I have still a lot. So this will be degrees of freedom for phase 1 and 2, or 0 and 1, I'm sorry. And then the degree for the divergence and for the rotation. And then you have in 3D, I don't give you the picture in 3D, and then you have the edges in which you work. In 2D, essentially the face and the edge are just obtained one by the other, a rotation of pi over 2, and the same for the degrees of freedom in the picture. Okay, come on. And in 3D, instead, you have here to use a Vem on the face, edge Vem. And these are the degrees of freedom. Then for the volume elements, those are, the most easy ones because you don't have to be continuous, so you took polynomials. And then what do we do for plates? Now for plates, plates are sort of fourth order guys. So you have to match the function and the normal derivative. So you have to choose the degree of the polynomial of the function and the degree of the normal derivative. And then inside you say, okay, I take the B by Laplacian to be of degree k minus 4 in order to have all polynomial of degree 4, k. Okay, and so as degrees of freedom, you take the values at the boundary that allow you to identify the function and the normal derivative, and then you take moments inside again against polynomials. And you remember that we had those crazy triangles that were so expensive that go, they called liver oil. Here you can do elements with that shape, and we assign, at each node, you prescribe the function and the two derivatives, and that's it. Or you can have this sort of a pack plate. This also is invented, and then on each vertex, you have a function and the two derivatives. On each midpoint, you have the function, the normal derivative, and the normal tangential double derivative. But again, the shape is not a problem anymore. Okay. Now, how do you work with that? The very last part, okay? I will just give some idea. The problem that you will surely have in mind, listen, you have a lot of functions that you know that they exist, but you do not want to compute. So how can you manipulate them? And the idea to manipulate virtual elements is to just use the degrees of freedom. So the information that you have, and see what can you compute out of the degrees of freedom without solving in an approximate way your problem inside. And in a sense, so it's sort of like, robotic surgery. You don't touch yourself, but you go with some artificial hands. And so, for instance, just an example, okay? If you know a function on the boundary and you know its average, then question, can you compute the projection of the gradient of this function on polynomials degree 1? Okay, answer, yes. You just integrate by parts. Okay? When you have to compute this integral there, the gradient of v times a polynomial of degree 1, vector polynomial, you integrate by parts, and you have on the boundary v is known, so there's no problem. And inside, the divergence of Q1 is a Q0. You know the average of the function, so you can compute. Okay, so this it's always like that. Okay, of course, more complicated, but the idea is this one. And so what do we do with that? Okay, now another remark which is extremely important, in particular for, say, applications to those conservation properties, is that with those families, of course by adjusting the degrees of the polynomials, because when you take the derivatives, the degrees goes down, the gradient of a nodal VEM is an edge VEM, and the curl of an edge VEM is a face VEM, and the divergence of a VEM, a face VEM is a volume VEM. And moreover, you have a sequence is exact. So, and okay, this is more for, believe me if you are not in the field, this property is essential to give you conservation properties of the final method that comes out. Okay. And so the basic instrument, I told you that essentially we want to compute the projection onto the polynomial, L2 projection on polynomials. And basically what we can do with this family is to compute the L2 projection of those functions onto the polynomials of a certain degree. You possibly notice, I kept repeating, the degrees of freedom that we take are already projection on polynomials at the moment. And then the ones that are lacking, you compute by integrating by parts. And so you can compute a sort of a scalar product, and then a scalar product which coincide with the true scalar product whenever one of the two entries is a polynomial. This is the property that will make your method exact on polynomials. And of course, you need some stability. And therefore, you end up with this trick by having some sort of I wouldn't say approximate, a surrogate L2 product. It's not approximate in the sense that if neither one is a polynomial, you just put something crazy. But it's not even approximate because when one of the two is a polynomial, what you compute is exact. So it's something which is, and very roughly is, so if you can compute the projection on polynomials, then your scalar product will be the projection, this you can compute, and then identity minus projection, but this you cannot compute, but you take any bilinear form which is symmetric and positive definite to take care of this. This is just for stability, okay? And so, okay, how do you use those scalar products? Let us consider, say, Darcy law, which is basically, again, the Laplacian, divergence of K grad P, and then you look at the variational formulation, and then this will be for the continuous problem, and down there you see the gradient of a nodal is an edge. You know how to compute a scalar product on edge elements, and so you use it. And instead, on the right, you know how to compute the scalar product of nodal, and again, you will approximate your right-hand side by a nodal, and then use the nodal scalar product. And the same if you want a mixed formulation. Okay, I go quickly. And then you have the discrete mixed formulation. You see here you have two equations, and then you replace the inner product by this H inner product, okay? in phase, volume, and so on. So basically, once you know how to do an inner product, you survive. Also, you know, for instance, magnetostatic problem, you have, say, above you see the continuous variational formulation, and below you see the discrete ones, in which you have just, you put the suitable type of inner product. So your unknowns are edge, so the curl is a face, and you use the scalar product of face. Okay, so basically this is more or less what I wanted to say. I want to point out that this is a really new method, and I did not reach my age of 69, still believing that there could be a method for all seasons. So I'm sure that there will be zillions of problems in which my beloved virtual elements will not apply, okay? But I also believe, since they are so robust and so ductile, that there will be many problems in which they could help. So now there is a work to be done in order to just understand which are the good ones and which are the bad ones, and also among the bad ones, the very bad, among the good ones, the very good, and so on. So there is work for everybody. Okay, thank you for your attention.
Thank you very much, Franco. Questions? Time. Yes, please.
Two. Well, the idea is that still to use the projection. So as soon as you have to compute, say, minor Laplace u plus u cube is equal to f. So you want a u cube, you will take the projection of u on polynomial degree k and then take the cube of the projection. So you go down to a polynomial and then you apply your function, your nonlinear function to the polynomial. This is what we have in mind, and we did some trial, you know, like, you know, Navier-Stokes, we did some trial, Navier-Stokes works, and actually the minus Laplace u plus u cube, it works. But there we still should prove, you know. There is, you know, there are two levels. The level in which you see that it works in a certain number of cases, but then you have to cook up a proof that tells you exactly what are the cases in which it will work. And this sometimes is the easy part, and you just have to invent the method. Some other times is the difficult part. There was another one in... I'm sorry?
I was also going to ask in the nonlinear case.
Ah, okay.
It seems to me that this would lend itself very well. You have control points, control data that you then use in order to use your method, that this would lend itself to a multi-resolution analysis where you would work coarsely and go to additional detail finally.
Yes.
Is that correct?
Yes, yes. I mean, there is people which is particularly interested on this aspect. And say, okay, yes, we will do so. Okay, but please do. we didn't see the answer so far, but but they were since they are doing this type of, for instance, multi-level, multi-scale, and so on. They were particularly interested because here you see, have you seen the connection in between, the coarse, the very fine grid and the very coarse grid? This, gives you a possibility that other methods do not. So.
Can you comment on a possible generalization, for instance, accounting for equations with variable coefficients?
Ah, yes. Okay, I forgot to tell. Well, actually, we are working on that, and it's basically is almost finished. I mean, the paper is in the final stages of preparation, and the numerical experiments are very good. So basically, the idea is that you take the projection of your, say, gradients or vectors on polynomials, and then you have the variable coefficient that you also approximate as a polynomial. So what you have to compute is a product of polynomials, and of course it will not be exact computation anymore, but then when you have a variable coefficient, you basically give up the idea of having exact computation. But and then you work.
But the actual idea is to replace a requirement on the fact that the Laplacian be in a polynomial space with the fact that the equation itself be the differential operator.
No, you keep the space as it is.
As it is, in that case.
At least what we are doing now. But there are so many possible variants that maybe we are just taking the wrong direction and somebody else will say, oh, well, those stupid guys, this was the way we had to go. That could be, it's a young method. But as far, you take the space as it is, and then there have been attempts like that for mimetic finite differences, in which you change somehow the definition, not really of the space because they don't have the space, but and then you just approximate when you have, remember that I had integral of, say, k minus 1 u, projection of u, projection of v. Basically, okay, projection of u is a polynomial, projection of v is a polynomial, and k minus 1 is also a polynomial because you approximate as a polynomial. For instance, if it is a smooth function, you take at one point and you take, say, Taylor expansion. Or otherwise, you take some other approximation of it by a polynomial. So, thank you.
Right. So if there are no further questions, I'd like to ask you to join me to thank again the speaker.
Thank you.
And to present the gift.